This might look like a simple triangle, but this shape is one of the strongest structures in engineering. Unlike squares or rectangles, triangles don't easily bend. That's why engineers use triangular frames in buildings such as roofs and towers. This simple shape helps buildings stay strong during storms and earthquakes. Look around the world, from massive bridges in Asia to skyscrapers in New York to communication towers across continents. Millions of structures rely on triangular designs.
This graph compares how two types of building structures respond to increasing earthquake forces. On the x-axis, we have the earthquake force intensity level from 1 to 5. On the y-axis, we measure the amount of building deformations in centimeters. The blue line represents a building with a triangle brace structural system, while the orange line represents a building with a rectangular frame structure. As the earthquake force increases, we can see that the rectangular frame structure deforms much more quickly. For examples, at force level 5, the rectangular structure deforms about 7 centimeters, while the triangle brace structure deforms only about 2 centimeters.
A simple three-sided shape helps cities stay strong, safe, and resilient. Without triangles, much of the infrastructure that support modern life would simply not stand. Look at that lamp. That lamp uses a solar panel to produce light. Geometry doesn't only help cities stay strong, it also helps cities produce clean energy. Solar panels generate electricity from sunlight, but their performance depends on one important thing: angle. If the panel faces the sun at the wrong angle, much of the sunlight is lost. But when engineers calculate the optimal angle, the panel captures more solar energy. This graph shows the relationship between the angle of a solar panel and its relative energy output. As we can see, when the panel angle increases from 0 degrees to about 25 degrees, the energy output also increases. The energy reaches its maximum around 25 degrees, which means this is the optimal angle for capturing sunlight efficiently. However, when the angle continues to increase beyond 30 degrees, the energy output starts to decrease. This happens because the sunlight no longer hits the panel directly, reducing the amount of energy absorbed. This shows how geometry and angles play an important role in renewable energy systems. By calculating the correct angle, engineers can design solar panels that produce maximum energy and support sustainable cities.
Mathematics, especially geometry, helps us build a more safe, more efficient, and more sustainable city. This idea is closely related to SDG 11, which promotes sustainable and more efficient development. This demonstrates geometry is not just a theoretical concept that learned in the classroom. It is a powerful tool that helps engineers, scientists, and planners design solutions for a real-world challenge. Through mathematics and innovation, we can build cities that are safer, smarter, and more sustainable for the future generation.
This is geometry at work.
This is geometry at work.
This is geometry at work.